So in this problem, we're talking about graph theory. And when we talk about graphs, we talk about vertices and edges. So vertices is the plural of vertex. So a vertex is going to be a point. So this is a point. And an edge is going to connect two vertices. So that's an example of an edge. Now, how we define the order of a vertex, whether the order is odd or even, we define the order by the number of connected edges. So, for example, if we look at this line that I just drew, from vertex A, there is one connected edge, and from vertex B, there is also one connected edge. But let's say we got a little crazy. And we drew something kind of nuts. Okay, so we're going to label all these vertices. So we'll say the order of vertex A. So you have one edge coming out here, one edge coming out here, and another edge coming out over there. That's going to be order of 3, so that's an odd vertex. For B, you'll have one edge there, another here, a third edge, and a fourth edge. So B is going to be an even vertex. For C, you're going to have 1, 2, 3, so C will be an odd vertex. For D, you'll just have 2. It'll be an even vertex. So let's take a look at the problems we have here. The first one is asking us to give an example of a graph having no odd vertices. So we only want even vertices. So an example of that would simply be a triangle. If you have A, B, and C, you can see that vertex A has 2 edges, B has 2 edges, and C has 2 edges. So this is an example of a graph having no odd vertices, since all of the vertices in example A are even. So for B, a graph having no even vertices. So this is going to look a lot like the example that we did before up here. If we have vertices, vertex A and B, there's only one edge connecting vertex A and one edge connecting vertex B. So this means there are no even vertices, only odd vertices. So I'm going to go ahead and skip over C for a second. We'll continue working. For part D, exactly one even vertex. So we saw that we had even vertexes when we drew a vertex with 2 lines. So we'll start there. Vertex with 2 edges. Now if we just put a vertex at the end of each of those edges, we'll label A, B, and C, and we'll count our edges. So A has 1 edge, that's odd. B has 2 edges, that makes it even, and C has 1 edge, which makes it odd. So this satisfies us having exactly one even vertex for part D. For part E, exactly 2 odd vertices. So, like we said before, the triangle gave us exactly 2 odd vertices. So the triangle gave us 2 even vertices. But I experimented to see what happens when we draw 2 triangles together. So if we draw triangle 1 and then triangle 2, we'll label these vertices. So for A, you have 2 edges. B, 1, 2, 3. C looks just like A, so we'll have 2 edges. And D looks just like B, so 3. So we have exactly 2 odd vertices in E. And actually, E satisfies the same requirements as F, because we have exactly 2 odd and 2 even. But if you want another drawing for F, we can draw 2 points and connect those 2 points. And really what's important when we're connecting these vertices with edges is not what the line looks like. The line can look like this. It's just the matter of the line connecting one vertex to another. So if we look at another example of F, A, and B, you see that there are 2 edges leading away from A, 2 edges leading away from B. So that gives us exactly 2 even vertices. Now, we'll go back to part C, since we skipped over that. Part C says exactly 1 odd vertex. It's not possible. If we draw a vertex, we have it here, but since there's no edges, we can't draw. We simply can't draw it. We can draw that, but that doesn't really count because you'd have to end that in a vertex, and that's exactly what we got for answer B, no even vertices. So you can try all sorts of combinations that you like. I drew all sorts of weird, funky combinations, but it simply isn't possible to draw a graph with exactly 1 odd vertex.